Okay, good morning, everyone. We're going to get started. I think if people are coming in, there's plenty of seats around. Please come find your seat. So welcome, everyone, and to our Saturday Physics for Everyone lecture series. As many probably know from looking at all the flyers, this marks the 30th anniversary of this public lecture program. And to commemorate this special event, we've invited a very special guest, Professor David Hertzog, who actually founded this program back in 1993. So Professor Hertzog was a longtime professor at the University of Illinois in our physics department. In 2010, he went to the University of Washington, where he's now Arthur B. McDonald Distinguished Professor of Physics, and also the director for the Center for Experimental Nuclear Physics and Astrophysics. His group has done really seminal work in the area of particle physics. We're going to hear about one subatomic particle called the muon and the so-called G-2 experiment that he's going to tell us about. He has a very distinguished career with numerous awards, including the Tom Bonner Prize in Nuclear Physics, the John Simon Guggenheim Memorial Foundation Fellowship, and the American Physical Society Fellowship. So it's a great pleasure to have him back on campus to tell his story. He's asked that we hold off on asking questions until the very end. And well, let's give him a big welcome, and we look forward to hearing his story.
I can't tell you how meaningful this is for me to be able to come back here. When you start your career at a wonderful institution like the University of Illinois, and in your very first big teaching assignment, you have this room with 300 students in it, and you're teaching a course called Practical Physics, How Things Work, which is for non-scientists, which I was assigned to do shortly after I arrived. And it was a fantastically fun course, lots of things in physics of music and sports and kitchen stuff and everything and so on. And my wife would always say, how can you teach a course called How Things Work? You can't fix anything. And I would say, I know why they work, I don't know why they don't. So it is a pleasure to be back in this room, and I'm going to tell you a story that I hope has sort of two levels to it. Some of this is technical because it is about an experiment that has been quite impactful in the last few years. But the overarching arc to my story isn't about this particular experiment, but it's a little bit more about the scientific process. So you can catch yourself finding wherever it appeals to you and resonates with you like that. So let me just begin. And I call it rocking the world with muons, and we'll start with that. So basically, in April of 2021, this story that I'm going to tell you really made worldwide news. Fermilab got the news out, but it was in the headlines of papers all over the world, as you can see by the many languages here. And in fact, if you really wanted to understand what this was about, you could go to this wonderful PhD comics, where I think the story is written more beautifully than most of us on the experiment could ever tell. It's really quite nicely done. And so what the buzz was all about was really, I've simplified this particular plot of things here. And essentially, the standard model of particle physics, the theory that has grown up for decades and decades and decades, which tells us what the particles and their interactions are, can predict this particular value of this number of the thing I'm going to talk about later. And so there's a painting of on some scale here of their result and their uncertainty on it. And way back when I was at Illinois here, we measured this number, and this was in 2004, and this number really is more recently, a few years ago, number updated, or it's been updated. And so this gap to here was already big, and everyone was wondering for a long time whether this was right, because it was simply one measurement or so. So that in 2021, when we opened the box in the experiment I'll tell you about, because we do these things blind, keep that in mind for later, we ended up more or less exactly confirming that. And then when people, statistical people, put this significance together, they say this is about 4 standard deviations, and then that calculates to some probability that's a fluke, which is pretty small, and it looks pretty interesting. So yeah, way back in the day, this was our group then, and this is myself and Paul Debevic, who's here in the audience. Paul and I started the experiment from the point of view of the Illinois team anyway. We didn't start the experiment and such, and here we were standing on one of the storage rings at the time. Here's another picture with my colleague Peter Campbell in the group, and some other people, Fred Gray in the group, and Paul back here, and so on. And it was, you might recognize this is right outside this room here. And it was really a wonderful time where we built lots of equipment for that other experiment. We were very proud of the result, and we analyzed that data. And so the new result as well. So then this August, just 2 months ago or so, we released another batch of data. The first thing that our experiment did on that first press release really was only 5 or 6% of the data that we have now taken. It was just a taste. It was just in a taste of the data, we had reconfirmed it. This time it's a bite. It's 25% of the data right now. And again, I'll show you the result at the end, but the result was interesting in the press. Some press said we did a great job and we're closer to a thing, and some said, looks like it's a problem, so you'll see why. It's a complicated, controversial ending to this story, which means the story will go on again. So let's start now at a kind of a beginning. So what did we measure? What did we test? And how did we do it? In real short answers. So 3 quick answers. We measured something the word that you'll hear called the gyromagnetic ratio of the muon, or we'll just say this letter G. Don't even need the muon thing there. Just this thing called G is going to show up today. And that'll be something that we talk about a little bit. And then what are we testing? We're testing whether what we know on what's called the standard model of particle physics is complete theory. Do we know all the particles? Do we know how they interact? And so on. And the theory, as I said earlier, it predicts this number very, very precisely. That you could see the size of this thing. And I haven't explained how precisely yet, but I will. And we measured this different one. So the difference between what we measure and what they predict says something's wrong or something's missing. The interpretation is the standard model doesn't have everything in it yet. So that means there's something new in terms of physics. And to put it in perspective now, the results that we talk about, the one I'm going to mention today, the updated, has a precision on a number of 200 parts per billion precision. So this is hard to wrap your heads around how small this is. And eventually, when we finish the data set, it'll be more like 140 parts per billion or better. So let me give you an idea about that in a moment. So you saw maybe that I said the experiment is called G minus 2. So I told you about G, but now why 2? Why 2? So basically, we determine this quantity here. This is the G number. If you memorize this, you could probably break into a lot of bank accounts by collaborators of mine who have used this as a password by now. So I'm assuming that this would be, fair game to start. So we measure that number, but you see the 2 sitting out there, and then a couple of zeros, and then some other little numbers here. If you subtract the 2 from it, then that's actually what we do. So we actually measure the difference. We measure this little bunch of numbers here, and we measure this bunch of numbers to 140 parts per million, let alone the 2 out front. That makes it even 100 times better. So to give you an idea what 140 parts per billion is, this was the picture on the front of the slide. And being Fermilab and having like a PR department, they made a 1,000-piece puzzle out of this that you can buy. I have one. I have not opened it. It looks way too hard to do 1,000 things. But my theory colleague, Steve Sharp at Washington, is a puzzler, and he did this puzzle, and he sent me this result, but he was very upset because 3 pieces were missing here. So that's 3 parts out of 1,000 mistake has been made in this puzzle. Maybe it was a dog, a cat, or whatever happened, but in any case, there was a 3-part problem. But if you would take this puzzle now, and you would shrink it down and multiply it by 132 puzzles, so you really got way into this now. You really want to do puzzles. And then if you lose just one piece, not 3 pieces per puzzle, but one piece out of 132,000 of these things, now you're at 7,000 parts per billion. And that experiment is so old school, it was done in the mid-70s at that precision. So you have to do more than that. Now you need 7,000 of these puzzles. This will keep you busy through your retirement years. And if you build them all and you only lose one piece out of all of that, now you're at the level of about an error of 140 parts per billion. So this would put it in perspective for you. It's not too easy to intuit these kind of uncertainties. So I'm going to now take you way back to the past and hopefully not completely butcher this story, which is a very beautiful story that takes quite a long time to tell in its fullness. But it'll start by talking about magnets and magnetism. And I preface this story in an audience like this, or physicists even, that say, when we go in to begin to learn our schooling in physics, we get taught everything that's known up until the time we walked in that classroom. So we don't know it in some order of who learned what before they learned that, and then this happened then. We sort of like, it's all gathered up, it's packaged neatly. So we learn about electricity and magnetism that was really developed through the 1800s beautifully, and classical mechanics and quantum mechanics, and all of this is sort of packaged together as this is where we start and we go forward. But if you look at it from a different perspective, like physics historians look at it, they actually sort of see the sequence and the thought. And that's part of the idea that I wanted to tell you about. And in particular, in the early 1900s or so, they knew everything pretty much about magnetism, electricity and magnetism. The laws of Maxwell were known, and Faraday and Ampere, and all these guys, they were old and done and so on. And we knew that a magnetic field was produced whenever an electric charge was in motion. That was a fundamental part of it, that was causing a thing, and it could cause what's called a magnetic moment, if you want. So this was known very, very well, and we know that from, kids know this, so you take this is like a typical thing that you might do for a grade school science project. You put a little battery and you make a little electromagnet, or you make a big version of your, you really liked that project when you were 7 and now you did it when you're older and you made this one. Or you went into medical field and you had a big MRI magnet and so on. So all of these are made with currents that make magnetic fields. But at the time, the puzzling thing at the time was, what about this bar magnet here? What is making this magnetic field in this bar magnet that's not connected to any power supply here? There's no obvious current in there. And there's definitely a field around that. They knew all about that very, very well. So they were conjecturing, and they didn't know any of the microscopic physics that we know now. And I think carefully, they didn't know about that. And this was really actually a fairly raging debate. And the raging debate was discussed in a way called, that I think there's a short version of this is basically, there must be something making a circular rotation of charge. That is how we think about, at this time, the creation of a magnetic field. So in 1908, Richardson, he was at Princeton, suggested a method to test for electron currents. The idea of the day was, somehow they knew about electrons, by the way, at this time. They knew about electrons, the cathode ray tube. So they think these things have to be zooming around in some kind of a circle thing. And so let me look at this animation for a minute, and this is a thing we would show. If you have an electron which goes around in a circle like that, then it will create a magnetic moment, which is its current times the area of the circle. And if you put in a couple of factors in there, it's the electron's charge, its velocity running around, it's the radius, and there's a 2 there. And if you actually also think about it going around, it causes something swirling around, has an angular momentum. And again, it's mass, its velocity, and its radius. And if you take a ratio of those two, the magnetic moment over the angular momentum, you get a factor here, E over 2m, and this E over 2m, notice that it has nothing to do with the radius anymore. It's canceled that out very nicely. And in fact, this was kind of, believe it or not, kind of known stuff. This kind of ratio was a known idea. This is neat because it doesn't matter whether it was a great big circle or a tiny, tiny little circle, this little factor would be there. And so then the idea was, okay, if you stick a little g, remember the g? If you stick a g out in front of that thing, then g would have the value of 1. Okay, g is 1 for this little system, and that was the idea. So how could you now test this idea? Well, we do know that if things behaved inside this magnet like that, then there should be some g equals 1 kind of result. And how would that appear? Well, the idea was actually, of all things, measured most precisely and early by Einstein. A fact that very few people, including myself, didn't know till about a year ago, that Einstein interrupted his work on general relativity for a few years to do experiments. So Einstein and de Haas did these experiments, which I'll describe very, very briefly, in order to seek the answer as to whether g was equal to 1 or not, which is he was passionate about this idea, not only for this understanding that he had, but for other physics beyond that, about zero-point energies and things like that were important to him. And so what the experiment is, and now this is a cartoon of it, but it was, the deeper you understand, it was a very elaborate experiment. So the idea is essentially falls out of the idea of the conservation of angular momentum. And you take a magnet like this one, and you hang it on a long, thin wire. And this is then a gadget that's now in a very special place where you make no external magnetic fields and so on, and you try to do vacuums and things. And you hang that iron sample like that. Maybe not that, it could be a demagnetized version of iron, sorry, not exactly that bar magnet. And you hang it like that, and then you have a little mirror on here to see the tiniest rotation like that with a beam that's going in and out of the thing. And you wrap a wire around this thing where you're going to then induce the magnetism inside this chunk of iron. You're going to induce it to line up. And if you induce them to line up like that, and then you believe in this concept of the angular momentum ratio, the thing is going to turn in the opposite direction to conserve angular momentum. So this idea from Richardson said, assuming that the magnetism of iron is due solely to the motion of negative electrons, the torsional reaction should easily give a measurable effect. And that's an understatement, to say the least, when you come up with the numbers, easily part of it. And by the way, I want to tell you that for those of you who really want the real story of this book, I've torn this book apart reading it multiple times when I tumbled into it. Many of us have this book called How Experiments End by Peter Gallison, and don't read it, because we think someday our experiment will end and we'll read it. And it's not about that at all, it turns out. It's turned about, the whole long first chapter is about the measurement of g. And the second long chapter, Paul, you would love to know this if you don't know this book, is all about the discovery of the muon for 100 pages. It's like, okay, I should have had that one. Here's the current. Notice this, I just threw the switch. Through the switch that drives the current, that makes a magnetic field, that makes a magnetic field, the thing turn, and you see a little deflection. How they did it was a little trickier than that, but this, the essence of that, they did it with resonances and things like that, but it was still, the idea was that. And so what did they get? So Einstein knew g equal to 1 had to be true. He believed this firmly in the idea of what they called molecular currents at the time. And in fact, he got that. He got g equals 1 to 10%, and everyone was happy. It's a nice paper, it's a long paper, and here's a little plot that you can see the rest of the plot's coming in 1950 with their number on it. And so, yeah, it's a good, the guy really does experiments and theory. And, okay, so, but it was wrong. And it was completely wrong. And the interesting thing was, over the next 10 years, slowly other experimenters were doing this. Over in Princeton, there was a grad student named Stewart who did this experiment. He did it very, very carefully, and he got 2. And so some of them were getting 2. So if they got 2, and now Einstein's like a heavy name to drop kind of a thing, and so you go, okay, how could it be 2? Well, if the electron is going this way, and if the nucleus is going the other way, and it's positive, the 2 of them together make 2 things doing that in the same, and there's 2. So a lot of them believed, okay, that's the idea, it's 2. And it went like that for a long time. So you can see all these 2 numbers here. And then it wasn't, of course, until mid-20s when Dirac's theory of the electron having an intrinsic spin, not a circular current that's running around like that, but its own intrinsic spin, the idea of this quantum object that we all finally understood, that is actually why it's 2. It's 2 for the electron being a point-like bar magnet like that, not a swirling current, is 2. And it turns out that, of course, the number in the end, for people who eventually did this super precisely, like in the 50s even, it's with the piece of magnet, like a piece of iron, you get maybe 1.96 or something. And the reason for that is there's a little bit of orbital in there as well as intrinsic. So we try the intrinsic spin as that. The story here is kind of interesting, right? Because you end up looking at a firm belief in something based on some fundamental principles. You get a measurement, you think you've confirmed an idea, and then it sort of evolves over the next decades to a completely revolutionary explanation, which, as physicists now, from the day we begin to learn about particles, we immediately are told the electron is a point-like particle with spin. And so is the muon. The muon is a brother of the electron, and they're just the same. So let me fast forward to 3 more important discoveries without telling you lengthy little stories along the way. But the next one is the discovery of the muon itself. It's this 200 times heavier electron, completely unexpected, coming out of cosmic rays. The physics of the day was getting pretty sophisticated in terms of quantum mechanics and the expectation of what would happen when a charged particle like an electron would bash through detectors and plates and so on and so forth. It would what they call radiate and lose its energy. And there was quantum field theory in the early days that explained that. This particle didn't do that. It was blasting through bricks and just happily still there. And they got to a point when Oppenheimer was like, either our quantum theory is wrong or there has to be a new particle. Well, we know it's a new particle. Well, that's a short version of that long, lengthy story. The next thing is in 1947, the G factor, this 2.00 number that I mentioned a few times had to be intrinsic to the electron, starts to get measured with atomic systems extremely precisely, and we begin to learn that it's not just 2, but it's like a tiny bit different than 2 by about a part in 1,000, a little bit bigger than 2. And I like this line. This is the kind of way they wrote way back then. You know, aesthetic objections could be raised against such a view. You know, this is what, but we'll come back to that. In 1956, Madame Wu followed up an experimental idea by Li and Yang here, who are pictured here. And again, Li and Yang were dealing with the fact that there was particle physics data related to the way a particle called a kaon was being observed in the laboratory. It was decaying in funny ways. And they just couldn't get that right. And so they came up with this completely radical idea that physics had a left-right asymmetry problem. In other words, the right and the left were not symmetric in the laws of physics, in particular the laws of weak interaction physics, the way radioactive things decay and so on. And so that was this paper they wrote in '56, a question of parity conservation in weak interactions. One of the fastest Nobel Prizes was the turnaround of this thing. And in that paper, it's a great paper, I always have it in my classes that we read, they have recipes for 3 experiments, all of which turn out to be exactly working well. And right below, within a year, the colleagues at Columbia here, Madame Wu's experiment, and then back to back with that, this one I chose because it involves the muon with Garwin and Letterman and Wenrich. They basically, right off the bat, say, from this paper, it tells you the recipe, like going to a cooking class of what to do. If you stop the muons, they're polarized from pions, they spin around. When they spin around, they decay in a very asymmetric way. So they stop the muons and they have a spin this way. Then you rotate them in a magnetic field and they shoot their particles off in a very asymmetric way as you rotate them. And sure enough, within one weekend, they could fiddle around with their experiment that they had and see this kind of oscillation. Bam, they could prove that parity was violated. Very important. In fact, here at the University of Illinois, when I started another course here, which was the modern experimental physics course, we built this apparatus. Paul and I put together a lot of this stuff, and with Eugene here, so Paul, Eugene, and me, basically magnets, scintillators, and so on, and this still exists. it catches muons from cosmic rays. They're polarized. They rotate in a magnetic field we put around there. Because they decay in a funny way, we actually are able to reproduce this kind of a thing right here in the laboratory. Our undergraduates do that every semester in principle. If we were 48 years earlier with this idea, could have had it, could have had the money. Didn't get the money. The key to this idea is that the muon is just a tiny magnet. So just think to yourself, shrink this down, and the muon is this tiny little magnet. And this tiny little magnet, kind of drawn here, looks like a bar. It looks like a top. If I stick this little tiny magnet inside a magnet and spin it, it's going to wobble. Like its magnetism is lined up to the field up top. It's going to wobble around like that. And this wobbling around frequency here that you see is very important. We're going to measure that frequency that it wobbles to this number that I mentioned, like hundreds parts per billion precision. We're going to measure that wobbling. And we have to measure that magnet, too, pretty well. So you have to measure the magnet, measure the wobble, and that's what you do. So you remember a couple of slides back, I went over it kind of fast. I said, oh, they learned that G wasn't 2. It was like 2.002, blah, 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 blah. So why is it 2.002? Why is it something not 2? Well, it turns out that the muon's magnetism is affected by all the virtual particles that are in the world. So it's a sniffer. It's a sniffer for all the particles that exist out there in a quantum mechanical way that we like to do with this funny illustration here. It is sensing the quantum fluctuations of all particles that exist. And this, quantitatively, you would require quantum field theory to really understand this, but the cartoonish way of looking at it is just as well for right now. It is sensing, it is sniffing around. That's a gravity experiment, sir. So I will put that, and this is a return. Yeah, okay, so now here's my attempt to take one thing higher in a talk like this. I was trying to think, how would I explain that little thing I said a moment ago and didn't want to dance over completely, which is like this quantum field theory. There's a theory that does this. And what we do, what we learn as students of this when we're trying to take classes and so on, is we learn these pictures here. And these pictures are called Feynman diagrams, and they're named for Richard Feynman, who I think most people have heard that name of Richard Feynman. And I thought about it for a long time about, well, what is that? And I thought, this is kind of like a hieroglyphics. If you dug this thing up, centuries from now and saw this little hieroglyphic, it represents an action and something to do. This cartoon represents them. And so this first cartoon, which affectionately got known as the Schwinger term, because Julian Schwinger, another co-Nobel laureate who calculated, was the first to calculate this. He didn't have the diagram, he just did it in math, I think, at the time. But here's what this means. This little line on the chalkboard is the muon. So just think about, and this is time, so here's the muon. And this little wiggly thing here is the magnetic field. It's in this magnet for a moment. And then this little light blue one is the virtual thing, the thing that was wobbling around crazy like that a moment ago. That's one of those that can pop in and out of the world. And with this little cartoon, if you're trained in the art, having gone through Gordon's calculational field theory class or so, you can bang this number out as a graduate student, and this is what you would get, this little number here. And so Schwinger was proud of this thing. This is his gravestone. And instead of saying, he's a loving father, da-da-da, it has that on it. It has alpha over 2 pi on it, because that's the thing, that's the thing. And so since then, this process is so algorithmically precise. It's harder and harder to calculate, lots of algebra, but they have calculated more than 12,000 of these perturbations of this diagram. They're now drawn things like this. And so they know this contribution of these sorts of things 100 times better than we could ever measure it. It's just impossibly precise. Now, you can also do this with other particles. You don't need to just do this with, the wiggle was a photon, and some of the other things in there were electrons. But you can also do this with neutrinos and W particles and Z particles. These are called weak particles, weak boson particles. And you can do this with this blob where I filled it in solidly, which involves other harder to calculate things because you can't quite calculate this one. And so in the end of the day, this whole world of calculating all of these bazillion pictures and so on is kind of actually, interestingly enough, organized right now by Aida Al-Khadra, a faculty member here at the University of Illinois. I don't know if she's here or not today. Are you here? Hi, Aida. Yeah, so I don't know. She's to herd all the theorists in the world, and they meet all the time, this is a fraction of them, into a jamboree to figure out all of those little pieces is a real art. And in fact, Aida gave a talk here in 2019 on the discovery of the muon, which was very nice. And I don't know if you remember, Aida, but at the Q&A, and it's the link, at the Q&A at the end, you asked her, I think, would she bet on, how much would she bet that we confirmed the new number in the new physics? And you bet $100. So you owe her $100. Let's have it. We want to pay up. So you can also draw, you can be very creative with this kind of hieroglyphic thing. You can put the kitchen sink in here. The muon suddenly goes into a kitchen sink, and it goes back to a muon. Doesn't happen a lot, but it would change. It would change how fast it spun, or you could put something else in there. And that's why the logo of our experiment looks like this with this funny blob of G-2 in there, because we're looking for something that isn't already known to be in one of these hieroglyphic diagrams. Fair enough? You guys all with me? We're hunting for something new. So they knew this idea way back in the day, and so really fast, there were, the experiments I'm talking about is like 5th generation version of this stuff. Here's some physicists, Francis Farley and others, in the early days calculating, and they get a wiggle that looks like this. It's a better wiggle than the one I showed you so far. And then they started to put the muons in a ring going around, and they got a lot more wiggles. And the more wiggles you get, the better the precision. So we're going from this precision down to 265,000 parts per billion. You know where we're going at the end of this. And then they got better again, and they had a great idea in the mid-70s at CERN where they had some tricks to make the muons stay in there a little better, and they got 7,000 parts per billion. That was the first bunch of puzzles I told you, and that's why I mentioned that one. That was a good experiment. And then the experiment that Paul and I, and this very young man right here, the head of your department, was a postdoc on this experiment. He was a killer postdoc. We knew at the time he was going to ascend to high things because of his insights. Anyway, all of us were involved in that experiment, and that experiment reached 540 parts per billion. And that's where things landed. And at the end of that, that was way back in the day, 2004, and then there was nothing. It's not an experiment that you just put together. This takes a lot of stuff. And the theory was here at the time, and it kept improving and bouncing around. And so this is the one that Aida really led in 2020 as the kind of culmination, distillation. This is the agreed on theory, and that ended up being pretty interesting. So the question in the physics community has been, is this wrong, this measurement? Is that wrong, or is something wrong here? And so if it was right, great, but since then, people have been doing other experiments at the big colliders and all kinds of the physics that this might have implied, and nobody's finding anything. We're like all of a sudden like the lonely little crack in the standard model. So we were getting increasingly nervous like this that our measurement was wrong. I mean, really we were shaking because we do this stuff blind. But we thought it's time to do a new experiment. And the new experiment got formed in, well, around 2010, 2009, 2010, when I went out to Washington. This is in front of our fountain at Washington. And there's Paul, there you are there, by the way, as well. And we had a nice meeting there. The interesting thing about this group of people to do this experiment is it's not just particle physicists. It's nuclear physicists, particle physicists, atomic physicists, optical physicists, accelerator physics, and theorists in our collaboration. So it is a consortium of people whose talents are, and communities and funding and everything are very, very different because it's such an eclectic kind of an experiment. The idea, remember, was that the muon spins around. The muon spins around in a magnet. That's the fundamental thing we have to figure out. So the way we do this is we're going to stick a muon spinning beam into a magnet, and it's going to go around in a circle. So basically, if you think about it, it just happened to be that the folks back there left a football here, and I always just did love this here because I used to fling it to the back row like that and scare the heck out of the students when I was here. But this, has a spiral, and this one has a wobble in the spiral. So, if it's spiraling like that, and it's like that, and it's spinning, and it's going into the ring, and it's going to go around like that, except it's going to go this way, we're going to see that the pointing nose of this thing is going to turn ever so slightly. Okay. Touchdown. So, yeah, so it goes around like that, and that's the direction it's going is the way it's always going in the direction of the black arrow. But the direction the spin is going starts to go a little faster, and that's the whole ticket to this thing, that we measure that thing. That's the wobble frequency. Then we have to measure the magnetic field, and then we just do, Paul used to always say this all the time, then we do long division. This was Paul's line. Guys, when we're done, we do long division, which I used to enjoy. But we needed the magnet. So it turned out that this very, very fancy magnet was still in New York, and we wanted to do the experiment in Fermilab for various reasons. So I had to move the magnet. And to move the magnet is not a trivial thing. It's got coils of some 14-meter diameter and so on, and it can't be flexed more than a few millimeters. So this space shuttle moving company called Emmert got the thing. We sneaked it out the side door. We put it on a truck. We put it on a barge. We drove it all the way around here on water, through the arches. We brought it, sneaked it on closed the highways at night near Chicago, brought it down the highways with police trucks and so on, sneaked it through the toll booth, paid the tolls, and brought it to Fermilab where there was a huge party. And that was step one. That was just step one. And then we had to put Humpty Dumpty back together again. I used to tell that story in front of the committee. I said, then we're going to put Humpty Dumpty back together again. And I thought that was clever, like I think it's clever now. And now I realize it's not clever because I went outside and my colleague said, don't you remember the nursery rhyme? All the king's horses, all the king's men couldn't put Humpty Dumpty back together again. I went, oh no! But over the course of a year, we rebuilt the magnet and made it better. And there's a lot of pictures here of students and things in our shop. We made 7,000 little tiny strips of iron to mask the magnetism and smooth it out like a pancake. And basically, these are people making these things to make an absolutely incredibly uniform magnet. And now, back to magnets for a minute. How do you measure a magnet really well? There's a lot of a connection here to the University of Illinois, again, to MRIs, magnetic resonance imaging techniques. And so that's actually what's done. We use little probes that do magnetic resonance imaging, and they look like this for a uniform field. And we make a trolley like this, and a trolley drives around in the ring, and each one of these little dots in the front of the trolley is a magnetic resonance imaging probe, like you might do if you had a medical condition, but we're going to do it in a big magnet. And if you watch this animation, as this dot goes around here, this is where the trolley is, and we're making a first pass measurement. And when they're lumpy like this, the field is lumpy, and we have to fix it. And when it's smooth like this, the field is smooth. And so we're measuring this, and then we go back and shim. Shim is like shaving, and we do tricks to make that better and better. When we're finally done, we get an incredibly uniform average magnetic field that we know, eventually we know this thing to really 30, 40 part per billion precision when we, in the right way. Then you need muons. So at Fermilab, the idea was there's a complex of accelerators there, and basically it goes like this. They start with a big batch of protons, bam, like this, bam, and then we split that into 4 little bam, 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 okay, and then they go one at a time, and they hit a target. This is now 300 meters, and this makes pions. Pions turn into muons over the course of these 300 meters. We run them around this triangle 4 times, boom, 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 where all of the rest of the pions disappear, so we just have muons left. The muons then go into the ring, circle around. So this is a big deal. There's 2 kilometers worth of magnets, 1,000 magnets here to just upstream of getting these pure muons that are spinning just so into our magnet. So when they get in our magnet like that, they have to go around this circle. And as they go around, as I mentioned earlier with the football, the orientation of their spin keeps advancing. That's fine. And then how do we know that? We don't see them. We don't touch them. They're running around inside a vacuum tube. We don't see it, but they decay. And when they decay into an electron, they reveal which way they were pointing. And we do that by catching them in a bunch of detectors that I made here that all the way around like that. And they make a big light flash, and it goes like this. So there's a detector here. It looks like that. It's made out of these beautiful pieces of glass, very special glass. An electron bashes into them. It makes a beautiful short little pulse. If it's a big pulse, we know the muon was pointing at the detector. If it's a little pulse, it was pointing backwards. And so as the muon spins around, it's like big pulses, little pulses, big pulses, little pulses as the spin goes around. And when we start the data, it just collects like that. If we just take the big pulses, that's literally a few seconds of data, a few minutes of data in real time that comes online. And so we end up collecting, just billions and billions and billions of these things. It's enough to make you dizzy, so the plot, here's the plot with 4 billion of them, and this is the wiggle. And I think everybody in this audience can easily see that there's a wiggle there, and you could probably figure out the frequency of that wiggle if you worked hard enough. It's hard to do that actually in practice, but it's not hard to see that you could do that on the screen. Now the fun thing about this, and this is really what makes the experiment have integrity, we do all of this blind. And by blind, this is a culture that I've been involved in for my whole life, really, 30 years. Every experiment we do in a way that we don't have any way to know the answer until a week or so before you know the answer. And we do that because we have all of these frequencies, there's clocks involved. There's very precise clocks to make the frequency. And we have somebody come into a special control room and change the clock so that it doesn't tick at exactly 1 second. It clicks a little bit less or a little bit faster by about a small amount, 25 parts per billion or so, 25 parts per million different from a normal clock frequency. And only later are we able to find out how fast the clock was ticking and therefore actually figure out what the frequencies were that we were measuring all along, which is very beautiful. And so here's two guys that, these are like management at Fermilab. I don't know if you trust management, but we took, they were once physicists. So that's a theorist and an experimentalist. And they changed the clock. They write the numbers down. They put them in envelopes that they mail to me and others. And we have these secret envelopes sealed, date in, date out. And this is a whole clock panel that you can't even get into. You can't see any lights on it, and you have to have special keys. So throughout the run, we never know what it is. And then when this, unfortunately, a thing called COVID, so we all of a sudden were anyway analyzing this data at home. So we had to decide when the analysis was completely done. We're on Zoom. We have to vote. Has to be unanimous, a couple hundred people. I open up an envelope. Chris Pauly opens up an envelope. We check whether the envelopes had the same numbers. They did. We type it into some fancy program. Bam, the number comes out. That is exactly the moment we learn it, and then we immediately can't change it. We have rules that we cannot change that number once we undo it. So we're very, very patient before we do that. We're sure that everything has been checked. And so that was the number that you saw at the beginning of the talk. It was right here. And in particle physics, the discovery threshold is 5 of these things that we have 4 of right now. So we're like, oh, close. So what happened then? The aftermath in the near and far future. So since then, this was all the data I showed you, that. We now have this published. I'll show you that in a moment. And all of this is in analysis right now. It's not like on the couch analysis, but it's being analyzed. And so people have all kinds of stuff. Over the years, theorists have lots of ideas of why there's a gap in there, that white space between, they call supersymmetry, leptoquarks, axion particle, like 2 Higgs model. There's so many models out there. There's thousands of citations to this work. We don't care. As experimentalists, we don't care. Our job is to get the number right and figure out later what the heck it is. So I could talk about that stuff, but I don't care. It's like a lot of them have to fiddle with their models to make it right. Other people, this I care about more. Other people believe that the standard model might be wrong. Remember that diagram I showed you here with the blob here like that? Okay, so this is the problem one. This is the one that the entire understanding of this one is the width of this green thing. Everything else would be the thickness of a dot. The green uncertainty here is based on how well they know this thing here. And this involves something called strongly interacting particles, which you can't calculate too well. And so right around the same time as our first measurement, there was a group of people using a technique that actually Aida is a specialist in called lattice quantum chromodynamics, where you put the entire piece of physics on a massive supercomputers and you crunch and say, what did you get? And up until then, there are many groups doing this. Up until then, the precisions of these numbers were much wider than these bars here, like this kind of thing. But one group claimed, and so far only this one group has claimed that, right, Aida? Despite years of everyone trying, no one has claimed something with as small of an uncertainty as these folks. And notice how this number is kind of pretty close to this one. If that turns out to be God's truth, then we don't really have too much to say. If it's wrong, we'll find out eventually. So that was one thing. Disturbing, unsettling, but not confirmed. Then last, I should say, by the way, that there's another way to get this. It's very important. This data here, this result here actually comes from people making experimental measurements. It's called theory, but it's really based on measuring a lot of cross-sections of annihilation of a positron and electron to pions. That's what all of this is. These are all integrated things. So this number, I want you to think, this number was measured by people. This number was calculated by computers. And these are both related to the prediction. And then this is us telling the results. So that's it. The reason for that is then last February, in a very unsettling moment, when we didn't want this to happen, this showed up. And this is me looking at the new paper coming out. The new paper by a group in Novosibirsk, Russia, measured one of that same thing, and they got a number, not here, they got a number kind of way over here. They're the only ones over here. That means 6 or 7 experiments here would have to be wrong if they're right. But so far, it's a mess now. What do we do with that? You know, it's a good-looking measurement. Everyone's looked at it closely. It doesn't look wrong, but that can't be right and that right at the same time and that one right at the same time, so we don't know what's going on. So meanwhile, it's our turn now. So it's our turn now in the game to come up with our new number. So we revealed this number in August 8th, I think it was a 10th or so of this year. And Fermilab Run 1 was here. This was the Brookhaven. This was Fermilab. And then, bam, this was our new number. Right down the middle. Like, it couldn't be more of a strike. We hardly had to change any of the colors on any of the things here. So suddenly, we have reduced the uncertainty. Now this white space is even bigger. In fact, woohoo! This is now that magic 5 standard deviations. So if these people would stop doing the experiment thinking the theory is wrong, we'd be in Fat City discovering something new. So it's exciting. But how excited were we? Well, we were excited that we didn't mess up and we got 3 times in a row, like bullseyes. We keep measuring the same number here. But the reality is, they're banging our head against the wall because the theory doesn't look like it's here. It looks like, maybe it's moving, maybe it's crawling over toward us, and I just don't know what to do with that. So we're going to leave it, we're just going to have to leave it right there. This is the group of people, by the way, at ELBA, and before I go to my what does this all mean slides, I want to remind you that this was in a series of experiments that started way back here, each one getting more and more precise, iconically represented by this data with this beautiful wiggles and so on and so forth. So this was you may be wondering where that poster came from. What am I doing in the middle of that? But I hope by now you've understood the yellowy things around there is emblematic of the muons going around. And this was a photographer at the University of Washington for a talk I gave who had me standing in front of a thing for an hour and a half while lights were flying around me and blasting light at me. And anyway, photographers are into that thing. So perspectives and lessons learned. First of all, even trained experimentalists and brilliant theorists succumb to bias. So especially when the theory is so beautifully logical. So you realize why we must do this stuff blind. In fact, Aida's calculations are also done on the computer blinded. Because there's a lot of difference between if the number is here and the number is here and how you feel about it afterwards. The other thing from these 100 and some 20 years, the aha moments in science, they're really rare. You should not, as young scientists, expect to go into the lab, da-da-da-da, bam, you found something, the world has changed. It is a slow, grinding process of things that have to be confirmed and so on. It takes a long time to get stuff right. In our case, in our collaborations case over these many decades, all we can control is the quality of our work. Thus the blinding, the care, the precisions of all the stuff, the large number of people involved. And in 20 years, I think to myself, in 20 years, what will they be saying about this work? What will be the equivalent of the Dirac statement on Einstein's work? Someday will I be in a rocking chair and like, oh, that's what it was all along. I hope this happens sooner than then. But it's kind of the story that we're involved in. Science is a process, and it's a process of experiments and models and theories and testing, confirmation, and so on. And with that, I'd like to thank you by leaving with a poem that I asked ChatGPT to write about muons for you. And you're welcome to ask me questions as long as you like.
Questions from the audience? Here, I'll moderate.
Two parts. First, take you back to Einstein when he measured G equals 1. What was he really measuring when he got G equal 1?
If you look in the details of what they got, they didn't do anything. They had just little subtle experimental biases and problems in there that were overcome eventually. But they liked where they were, so they didn't kind of crack it. But they did a very, very good set of experiments. There were things about the magnetic material. If it saturates when they put the current on, then they don't get the linear effect that they had in mind. Stuff like that was happening. They didn't know how to zero the field in between. So the guy, Stewart, afterwards, instead of like swinging the magnet back and forth between two cycles of the polarity of the induced current, induced moments, they only went one direction, then back to zero, one direction, back to zero all the time. And then they flipped everything and went the other way and the other way so that they could be sure that they weren't getting effect of the Earth's magnetic field as well. That was a big deal, shielding the Earth's field. These rotations were microscopically tiny. You could only see them, these days you basically have a laser beam bouncing on a mirror and seeing a micro rotation of the thing. At our lab at Sempla Lab, we're pretty famous. I'm not involved at all in this and never was, but we're pretty famous for a series of experiments that actually do this kind of a thing for gravity. Cavendish experiments, that's things basically with masses that sit on these torsion pendulums that go around. It's very similar to the concept here. And they work really, really hard to do things that measure the weak equivalence principle, the value of big G, and things like that. So that's kind of the idea of the experiment. It seems like it just came down to, not quite good enough. Eventually people, Barnett and others, were getting two, and they kept at it for years and years with long lists of things, but they had the interpretation wrong. People that two had the interpretation wrong. That was the second part of that, which was kind of,
Part 2?
Yeah.
Could you give me the name of that cartoon from that physicist that you...
You can read it. Yeah. York, what is his name? I have to look at the beginning now. But anyway, that's the cartoon. There it is, York Chan, G-H-A-N. Written and drawn by that. The APS has that occasion. Okay?
More questions from the audience. Yep, right here in the front.
How do you figure out that the first experiment where you have to get the protons, basically to get the muons, and also related to that, how do you guys basically rearrange the world to bring this magnet to, or whatever it was, the Fermi Lab? I remember in high school, I spent a lot of time there.
At Fermi Lab? Or
yeah. They
Yeah.
made a big deal of how they brought it all over the country.
Right. So what's your question exactly on that part of it?
How do you get that to happen? 'Cause making something happen in this little place, it's so hard.
How do you make something happen like this project?
Yeah, just from that example.
Yeah, from that example, I can tell you that through many a snowstorm and many of, I don't know if this will work, I would be pounding my way with a colleague to Washington, D.C. to try to convince the funding agencies of the importance of doing this experiment in the early days. And then gathering up teams from around the world that had specialties and so on. And so we form a collaboration. It starts small and it grows slowly. And you have to go through hurdle after hurdle because it's expensive. It's $100 million or so, right? And you have to get that going. And then what you needed to do is all of a sudden you identify an individual, in this particular case, Chris Pauley, who was a PhD student here at the University of Illinois in my group, who became the project manager, who organized this kind of move from Emmert International. And so you start seeing money and engineers are involved in moving these kinds of things. You know, I'm just sitting there watching it at this point. I got to ride in a truck once. And all of us, meanwhile, all of us are building instrumentation. So all of the detectors that were involved in this, I built them for both experiments. So I'm back in the lab trying to figure out how to build detectors. And this guy's group is trying to build NMR probes, and somebody else is trying to build electronics. And all of that's happening in some kind of an organized way that marches along for 5-7 years or so until you finally are able to begin to commission it. I'm not sure if that's what you had in mind, but that's a bit about how these big things go, at least, in general.
Question in the back.
Hi, it started with electrons, we moved to muon a lot. Where's tau?
The tau, people think of, good question, he's asking about tau, which is the third lepton. It's a heavier one again. So the way the physics goes, and I passed this slide very briefly at the end, I had as a backup, but you know, why would you do this with muons instead of electrons? Because electrons, they measured this thing with electrons, you know, thousands of times better than us. Why not that? It turns out that that thing with the kitchen sink that you saw for a minute, you are 44,000 times more sensitive to those kitchen sinks if you use a muon than if you use electron. Consequently, if you use the tau, which is even a heavier one, you'd be even 100,000 times more sensitive to those kitchen sinks. But the tau particle lives for like picoseconds. You can't make a beam out of it, and it decays in so many different ways that it doesn't have this one singular way. The muon really does decay in this one singular way in which it gives off, it reveals itself, and it lives for, if it's at rest, it lives, well, okay, in this ring it lives for 64 microseconds. So 64 microseconds on our world, we watch it for almost a millisecond. All those wiggles take almost a millisecond to decay away. When you saw it going like this, it's just, the population's just disappearing slowly, and then we refill it. But the tau doesn't have that ability. Nevertheless, some people talk about trying to do the tau magnetic moment in colliders and so on, but it seems to me like just an academic exercise. There's no way you can put together something like this. Good question. Yeah.
Oh, right here. Gordon.
2 comments. Polycarp Cush was a PhD from Illinois.
Uh-huh.
Does anybody understand why Einstein was off by a factor of 2?
Yeah, I was just saying that. They really had just experimental problems like that. They were saturating the magnetism of the thing. They think that now. Stuff like that, the little Earth field things. Really just tiny little things. And they liked one. They were getting, they weren't doing these things always blind. He was so convinced of this. Some of the stuff he was saying afterwards and where he went with this idea was pretty strong. And he just wasn't going to go into the quantum side of life. Yeah. Okay, anyone else?
Maybe I'll ask the last question, Dave.
What was the inspiration for Saturday morning physics?
Good question.
Thank you for that. Do you have that answer? I can tell him. Because I was, oh yeah. So as a high school student in Pittsburgh, in a little tiny town that nobody went to college where I went, it's high school. I was invited along with the 3 other students to go on the north side of Pittsburgh to Westinghouse Corporation on Saturday mornings to the Westinghouse Science Honors Institute. We got in a car and we drove there, and it was just like this. There was like food, and there was somebody talking, and sometimes it made sense and sometimes it didn't make any sense, And one day there was a physicist there that talked about condensed matter physics, cryogenics, and did experiments. And I was just, what is this? This is amazing. And so I thought, well, I have to major in something, go to college, I got to do something. That sounds like a good something to start it. So the point of that story was, first, a moment like this can be very, very impactful for somebody you don't know. There could be somebody over there right now who's going, hey, this is cool, quietly, And when I got here, and David Campbell asked a few of us to think about outreach in the days before outreach ideas were even, the word was even used yet. I remembered this experience and thought this would be great for the high school students. And we brought in high school students a lot. It was full of high school students for years and years. I don't know. It's changed to now the community a little bit, it seems. But that was just the idea. The idea was, let's do that. And I used to do little vignettes here on the physics of sports and music and so on before the main speaker would talk. And so maybe you now do demos and so on,
yeah.
similar like that. But that was the idea. The idea was something like that.
I think that's a great place to end for today. So let's thank Professor Hertzog one more time for a great talk. So we have a full day of events today, and next I'm going to introduce Professor Matthias Gross-Perdekamp, who's the department head, who's going to say a few things commemorating this 30th anniversary of Saturday Physics for Everyone, and then there'll be cake outside to commemorate this. Matthias, do you have your slides pulled up? Okay.
Jan, thank you for introducing me, and I want to thank again Dave Hertzog for coming here and giving such a fantastic and smooth lecture. You have noticed how smooth he is. One thing I have to share, I was a happy postdoc at Brookhaven National Lab. I was working in an institute that was led by T.D. Lee when Dave and I met, and Dave shared the idea of coming to Illinois since it's such a great place. And I think after the talk that you just heard, you understand immediately why I came here. The only problem is soon after I arrived, Dave left for the University of Washington and took his beautiful experiment to Fermilab. So, but he left us with a legacy of Saturday Physics for Everyone. This is something he started 30 years ago. And I think this is a very good opportunity to say how impactful it was and to say thank you to everyone who has contributed. So the structure in the 30 years always has been very similar to what you see this semester. There have been 5 to 8 lectures. Here briefly listed the 3 lectures we already had this year and the 3 that are still to come. They are very high quality and often try to relate physics at the forefront of our research to a general audience. Here are a few people who I'd like to highlight and thank you. First, David Hertzog for being the first director for 2 years in 1993 and 1994. Then Inga Karliner, who is with us in the back, who was the director 17 times in the 18 years between 1999 and 2016. I also want to thank this year's director, Irene Lira Ansaker, who is in the back and has organized the events that you will follow today. Then I think it's also very special that we have one of the very first speakers with us, Gordon Boehm, who is here on the right side. And I want to also mention the 5 top speakers. I said it wrong, the 2 top speakers who spoke 5 times each, Scott Willenbrock and Brian Fields. No, they have to come back. So what is it? We had 173 Saturday lectures, and we explored physics from the beginning of time, the Big Bang, to quantum computers, one of our favorite pastimes at the moment. And these topics were presented by a very broad range of researchers and faculty from a broad range of departments. Among those were 4 lectures by Nobel laureates. Here you see our own Tony Leggett, and 16 lecturers who are members of the National Academy, like Gordon Boehm. We estimate that we reached more than 15,000 students. David commented that we don't have so many high school students in the room today. I think this still may have to do with the pandemic, during which for 2 years we discontinued this. But we really reached a very large number of students. And we are pretty sure along the lines that Dave described at the end of his talk, that many decided to become physicists or engineers. And I want to briefly tell you what it means or how it is to be a physics student here at Illinois. We have a very large class of 500 students in 4 years. And we are leading innovations in physics education research and in the delivery of courses. We think that we offer excellent physics education. And there is a broad and rich life of activities. This can be in student societies or organizations. Here, for example, on the top, I took some snapshots from Facebook, from our Facebook page, is Lab Escape at the Farmers Market in Urbana, or at the bottom right is Sam Lunt, who is also here and works in my lab, who won the Claire Booth Luce Research Scholarship that pays her research for a semester, including a trip to CERN to try out instrumentation that she has helped to develop. If you're a student and want to learn more of the activities that we have in the department, check out our web pages, the Facebook page, and also Instagram. There are lots of examples. The students do very well. I picked this, I think, from Instagram, from our Instagram page. Past spring, from our graduating class, 119 students, seniors, made the dean's list of students, and 55% of our students graduated with honors. That's a very high ratio. Our students work hard, I have to admit, but they also learn a lot and they do well. 50% of them move on to graduate school. The other half ends up in the private sector and do exceedingly well there. According to the American Institute of Physics, the average starting salary for a physics major who works in the STEM sector is about $70,000. So I want to also briefly describe for potential students what the nature of research is in Illinois. We are in the engineering college here. This is somewhat unusual. In most universities, physics is in liberal arts and sciences, or arts and sciences. We are in engineering, and that matches well our legacy of science-based engineering here at the University of Illinois. The intent is to find engineering solutions that are firmly based on fundamental science. And a historic example of great importance is the invention of the transistor and then the decade-long development of digital computers and finally supercomputers. I have a few examples on the right. You also see how this is very collaborative within the College of Engineering. And Illinois, basically for several decades, every 10 years had the fastest, or at least one of the fastest supercomputers in the world. We try to do similar things today. This is one example of many. Our new Illinois Quantum Information Science and Technology Center. I choose this example because we can make an analogy to the invention of digital computing. Here on the fundamental science side, this is where physics comes in the engineering college. We need to develop quantum bits that reliably can be used in quantum computers. And then together with our engineering colleagues, we try to integrate this into working quantum computing systems. That is one of the exciting opportunities that's open to our students. We have many others. I might mention the new Center for Quantitative Cell Biology that just won a $30 million NSF Science and Technology grant for exploring the quantitative behavior of cells. So I want to end, and we then go to eat cake, by inviting the students to study physics at the University of Illinois. It is great if Saturday physics for everyone has made first contact and has contributed to making you think about training in STEM. Thank you.